So all-flash arrays. What we're going to be talking about today is sort of where they fit within organizations. Give a little bit of conversation around that and see where it takes us. So the agenda, why buy an all-flash array? So we're going to look into, what drives organizations to move to all-flash. What use cases are there? And then we're going to talk about how is flash hardware different, right? So having a basic understanding of what differentiates all-flash arrays compared to traditional hybrid arrays can help put an understanding around some of the pitfalls, things you can run into, because it all does look very different and run very differently. Then we're going to talk about what to look for within an AFA, what feature sets are, how they can be different between vendors, what some of the misconceptions are, things like that. And then we're going to touch on how to evaluate an AFA. The traditional benchmarking isn't necessarily the best. The way things have been done in the past with a lot of the legacy storage. So touching a little bit on that and what the standards are out there these days. So why buy all flash? Let's start off by talking about where it lives, right? So right now, all flash is not something you're going to buy for every workload within your environment. While SSD has definitely gotten cheaper, it has not hit that point just yet where it's necessarily a viable or cost-effective option to be used for everything. So right now, you can see here, it's typically living in some of those performance-intensive areas, workloads, SQL, VDI, Oracle database, things like that. So something that you need pretty intense performance on, usually that's a very high I/O per gig is what you're going to want to see there. So hybrid arrays are still very much a viable option for the remainder of the environment. And then obviously you're going to have that cheap, deep archival. And flash on servers is not going to go away anytime soon, still used for very high performance computing. So I'll touch on why, all right? Why buy an AFA? I think a lot of times the hype gets in front of a lot of our customers when we're talking with it. It's just, hey, I hear AFA is the way of the future, so let's take a look. I want to see about buying it. And that's great. If you can afford it and the budget's there and you want all flash, get all flash. But when you're really trying to make sure that every dollar is spent as efficiently as possible, with definitely what we see more is shrinking IT budgets, understanding what the outcome of the AFA is going to be, right? So what outcome are you looking for? Is there a financial benefit that you can tangibly calculate by being faster? If we reduce the milliseconds from, for accessing certain application data, does that do anything for your business, right? Does that allow more transactions to come through faster, or does that provide a better end customer experience that sets you apart from your competition, right? Depending on what your business is, that could be any number of things. So really understanding what you're trying to accomplish, why the AFA is a benefit to you, is really the first step to really help you understand what the differentiators are between the various products you look at, but also is even a fit, right? Because the hybrid arrays that are out there these days can do a lot of IOPS. So if that's the use case, typically there's a few options to look at outside of even just AFAs. And for those who don't know, obviously all flash arrays are commonly referred to as AFAs. So what are a couple of those reasons, right? We expect data to be available instantly. In the world we live in, I pull out my phone, I look for directions. I don't like it when Google has to calculate that, right? I don't like waiting for my maps to pop up on my phone. Usually, and sadly, I think the majority of people end up doing this stuff while driving, right, which is completely unsafe. So the longer you're looking at your phone waiting for that to load time, the more unsafe you are. But that's the world we live in. We live in a world of on-demand. You want it, and you want it now, and you want it fast. Financials. Obviously, in the world of the stock market, microseconds matter, right? So when you say that we can improve performance by 10 milliseconds into sub-millisecond latency, On top of that, possibly microseconds, that's a financial impact directly to the organization, right? That's something they can tangibly calculate to help justify any cost increase it is to move to AFA. So what do we see from a lot of our customers in terms of why they're moving to the all-flash arrays? One thing we hear pretty often is our environment's slow. My end users are complaining. What can I do to really speed things up? So there's something referred to as the app data gap, right? So with the app data gap, what's really looked at is where in that path between the storage and the application is that data being slowed down. So evaluating that to figure out what the actual bottleneck is always going to be the first case. So what you're going to want to do is really run an assessment around that to find out, is there anything you can do to make sure that is where the gap is? Because in over 7,500 customers that were assessed, only 40% found that storage was the performance bottleneck within their environment in that app data gap, right? So there's all these companies rushing out to buy AFAs thinking to solve all their problems, but really the bottleneck might be in the network. It might be at the host configuration level, right? It could be a number of places outside of storage, and if you really understand that, it really is going to help to set the expectations in terms of what to expect. Because putting an AFA in and finding out you're not running any faster, I can't imagine too many things that would be a little more disheartening or unsettling and frustrating as something like that, because it's not an easy purchase. So that data gap that you can see here, really here are the various just examples of reasons, right? Interoperability issues, host compute, non-storage best practices. The non-storage best practices is probably one of the ones I see the most. With a lot of the legacy storage you see out there, there's so many options to configure, right? Do I do this application on RAID 10? Do I do it on RAID 5, right? What speed drive do I have? Am I calculating IOPS? Is the caching, with the SSD caching these days, is it really hitting the hot data that I expect it to be? So if there's one thing I see a lot of, it's non-storage best practices or storage best practice issues, but also issues around networking. Making sure that multipathing isn't taking you through some sort of loop, right? Things like that really can differentiate the performance level and make sure that latency isn't across that network. So how is Flash different? What is Flash doing that really differentiates it from traditional disk, right, to HDD? So this is important to know just from understanding how it works, what some of the pitfalls might be. So what's the difference between SSD and HDD? Well, pretty much everything. They are different in pretty much every way other than they both store data. So HDD hardware drives, hard drives store data on a series of spinning magnetic disks called platters, right? There's an actuator arm with a read-write head attached to it. The arm positions itself over the read-write heads over the correct area, and from there, it's going to read and write information, right? SSD is completely different. It's stored on interconnected flash memory chips with a controller to process and determine speed. From there, it essentially does electrons that store within something called a floating gate. Based on the charge, it's either a 0 or a 1. And I think we all know that all data is pretty much written and read in zeros and ones. So, NAND flash technology is organized in a grid. So here you can see in the picture, just even fundamentally from a hardware perspective, these are completely different. So they're often looked at, very similar. People know the SSD doesn't move, right? There's no moving parts, it's quiet. But they don't typically understand how it works and what that affects. So that's sort of a key understanding as we move forward and we talk about some of the pitfalls and some of the durability questions that have constantly been out there. Also understanding the different types of SSD that are offered to customers. So if you go test out one storage array or you see the price on one and then you compare it to another, right? the common question is, how am I getting the same amount of usable, the same amount of claimed performance for 25% less in price, right? That can be accomplished a number of ways, right? Different feature sets, but often one thing to be looked at is what type of disk is being used, right? So SLC, EMLC, 3D NAND, really more these days, are common disk types that you can see. The differentiators have typically been SLC's got the durability and it's got the performance, right? EMLC was really introduced to bridge that gap from cost, performance, and durability. So typically, EMLC will be, have a solid, lifespan from a durability standpoint, close to the SLC level performance, but typically you want to have a higher level read to write ratio. You want more reads than you're typically going to want writes. So that's probably one of the number one things to look at. 3D NAND has really come about these days, and you're going to see pretty much across the board, you're going to see mostly 3D NAND being used in a lot of products going forward, especially new products they're able to build from the ground up, because what they've done is essentially improve on durability while maintaining a base performance level that you expect out of a SSD drive. But the real differentiator is their ability to scale, right? So I'm sure most of you have either read in articles or seen in videos on YouTube about the 3 terabyte SSD drives, right? 1.9 terabytes here, 2 terabytes there, 3 terabytes. The scale's grown pretty significantly in a very short period of time. It was only 2-3 years ago that a 400 gig SSD drive was considered pretty big, at least in the enterprise SAN space, right? So the fact that we're already in the 3 terabyte plus range is a significant differentiator, and what's really allowing that is the fact that 3D NAND is being introduced. One key thing to know with SSD is typically the throughput on an SSD drive is nearly 10 times that of an HDD drive, right? So that being said, it's one thing to know that SSDs can do a lot of performance, but understanding the throughput capable of these drives is a key factor when figuring out capacity later. So the question always asked is, are SSDs durable enough to run Tier 1 production? Well, one of the reasons they've often been thought not durable enough is write amplification. So with write amplification, it starts off where an SSD is essentially empty, right? So every write's going to hit it, and it's going to be really fast. And it's going to move really quickly. That's not a problem. The problems really start when you start trying to overwrite existing data. So because SSDs read data at a page level, right, as you can see here, they also have to write at the page level. So assuming surrounding cells are empty, you can always erase data at the block. You can only erase data at the block level, right? So you can see here A, B, and C, and D were written. And there's other free space there, so that's not an issue right now. But this is an empty drive. That's going to happen really fast. Because that data does change, right now there's still empty pages available. So now E, F, G, H were written, and A, B, C, and D have been changed, right? So they're going to take up the rest of that block. Now, once you need space, garbage collection needs to happen. So we can't just write back into A, B, C, and D. What we need to do is take all of the data within that block, block X, bring that back into cache, eliminate the old data, and write brand new to the free pages on a new block. Now that's really key to know, and write amplification is a real problem for SSD. That's why one of the number one questions you're going to want to answer and know when you're looking at all flash is, what is my read to write ratio? And we're going to touch on a little bit more on that later, but because of this issue. The more this happens and the more data changes, the more write amplification is going to happen. And you can have all the IOPS in the world, but if this has to happen in the background, that's going to take not only CPU, but it's also going to increase IOPS exponentially. So making sure that your array can handle that needed write performance write amplification is the key. So now let's talk a little bit about what to look for in an AFA. So we're going to start off with the key performance metrics, right? I think everyone knows I/O. Latency is cared about a lot more these days than it was, let's just say, 8, 9 years ago. Typically, it was I/O and a little bit of throughput. Latency is something being looked at a lot closer than it was in the past. And throughput, right? What we're seeing also a lot of these days is throughput being a lot more important than it was even with past fiber channel environments. You never really had an issue. These days, the idea with data growth, right, with big data environments, with large block I/O, with extremely high performing applications, even with a lot of small blocks, if that adds up to be enough, throughput can often be the bottleneck. So one thing you're going to hear a lot of vendors talk about is average block size, right? The question is, what does average block size really do for you? Not much, right? When they're talking about average block size, that's really just to set themselves up to position themselves better for you. Because I don't care about average block size, I care about actual block size. I'm going to look at applications and figure out what they actually need. And I put this picture on here because if you look at the average size of a vehicle in this picture, it's probably like a Mini, right? A small car. But if I built a tunnel for the average vehicle size in this picture, do you think any of those buses or vans are going to be able to make it through? No. And it is very similar, a very similar situation when you're sizing out performance, especially on an all-flash array, right, where a bunch of small block writes can very, very much impact performance compared to, let's just say, one large block application you might have on there, or the significant factor of maybe a large stripe for backups might play into average block size. So average block size isn't really going to make much of a difference in your environment. It's always best to focus on each individual application. Then the question is, can the AFA handle multiple applications with different block sizes, right, without a performance impact? That's a question that is being asked a lot more. So I'd say, 2 years ago, 3 years ago, when all-flash arrays were a lot newer, the majority of people purchasing them were purchasing them for point solutions, right, to live in an environment of only one application. But what we've really seen over the last year and a half, a lot more, has been the use case around multiple applications. So making sure that you have an array that can handle multiple workloads despite block size, right? You don't want it to be, if you put Exchange on an all-flash array and you put SQL on an all-flash array, you don't want the 32K blocks to be eating up the majority of the CPU for deduplication or something along those lines. You don't want any challenges to come about because you use multiple applications. So making sure that you have each individual application's needs and making sure the array can handle each one of those applications at the same time is definitely a key thing to know. Read-write ratio. So this is something that is often overlooked, and the reason being, when it came to spinning disk, your read-write ratio wasn't nearly as important. You wanted to know it, but it might factor into sort of what type of RAID you do. As time progressed, it wasn't quite the factor it originally was. RAID 10 was being used sort of less and less depending on individual applications. But with all-flash arrays, a scenario like the one on the right can literally completely crash the array. An 82% write environment, I would have all sorts of questions before I put an AFA in there, because that's not what Flash is good for, right? Flash is not known for being the best write target. It's a read-heavy environments are typically going to get the best performance. And while it might not necessarily even crash the AFA, it's going to significantly reduce performance. So if you talk to most AFA vendors, they're going to give you their marketing information on performance. And what that really is good for is most of the time nothing. What they're going to do is tell you what their highest level of performance is. 100% read environment, right? That's not going to do much use for you. So you can see here, while some of the performance numbers on this are actually even much more improved over the last year or so, what this graph is a good representation for is the difference in performance between an empty drive and a full drive, right? So understanding that your AFA is going to change performance and that's going to evolve as it fills up, now the question becomes, what's the vendor doing to rectify that, right? What processes do they have in place to negate that performance issue that is a natural function of SSD? So this slide's a good representation of the ratio, right? And the fact that you can see a performance drop of nearly 40% between a full SSD drive and an empty SSD drive. Another thing is beware the checkboxes, right? A lot of the AFA vendors are all about having the checkbox for a feature set. They'll bolt on a feature just so they can say they have it, but then they'll tell you probably don't want to use this in production here, or hey, there's actually a little secret to how it works, things like that. The features are great if you use them. So the checklist, the high-level checklist, isn't always going to be ideal. So understanding your applications and what features will work with your workloads and exactly how they will work, right? It's one thing to say, hey, dedupe is great. But if my entire point of buying the AFA is to put SQL or an Oracle database on it with no test dev, what good is dedupe going to do me, right? Probably not much at all. So how that vendor dedupes is probably not a big concern of mine right off the bat. Now, if my plans are in the future to move everything there, yes, I might want to find that out now. The reality is, who knows what each one of those products is going to be in 2 years, right? What kind of software updates are going to be, what kind of feature set improvements. So really understanding what those features are, how you're going to use them, and how they work with the applications you're going to use them for is something that is very key to find out during that evaluation process. Feature control. So, can you turn features on and off? So you got that checklist, you've got all the features available to you, right? Now the question is, how do you turn that feature off, right? Is there an option, as my little animation doesn't come up, is there an option to turn that off? If I've got, like I just said, an entirely database environment, there is always going to be a penalty for deduping. They might say all the vendors are going to say, well, no, we do it at very high speeds. Well, the reality is, it might not be a penalty that's going to make it slow, but there's definitely going to be more CPU cycles and more speed available by not deduping, right? By turning compression off for an application that might not use compression. So if every millisecond matters or every microsecond matters, you might want to turn off a feature set to allow that performance to hit a top end, right? So some vendors don't offer that. Some do everything globally. So having that level of control can be valuable for a lot of customers depending on exactly what they're trying to do. So that's definitely one of the key questions you want to understand when you're evaluating different vendors is what granularity do I have control over, right? Can I have dedupe on for some and not others? Or is it on or off for the entire box? Is compression on or off for the entire box, or can I do it per volume or lung, right? Things like that are very key to know and understand before making a purchase. Deduplication, probably the #1 feature that's most talked about when it comes to AFAs. So understand the impact of dedupe on performance capacity. So like I just said, there's always a tax, right? Nothing dedupes without some sort of tax. So if you can understand what that tax is, that's going to put you in the best position to really understand where you want to use it, where you might benefit from turning it off, things like that. Also, is dedupe on all the time? So there's a number of vendors out there, like I said, that will put features into their product for a combination of checklists, but for also just to be able to say they have it at a high level, and they'll say maybe, hey, we do it in line. As in, for those who don't know what inline and post-process is, inline is when a block is deduped essentially at the controller level, right? It's not stored first, taking up capacity, then it's deduped. It's deduped as it's processed. So you're only saving deduped blocks, right? Original blocks. Post-process is where everything is saved originally, and then a process comes later, sometimes at night, depending on the product. It might be every hour, or when there's free cycles, and then it's deduped. Why does that matter, right? Well, why that matters is, SSD is all about essentially over-provisioning. You buy a 20 terabyte all-flash array, not with the intentions of putting, most people at least, with the intentions of putting less than 20 terabytes like a traditional array. You buy it with the intention of putting much more than 20 terabytes, right? 40, 50 terabytes, 60 terabytes, depending on your application, right? Most vendors have tout something along the lines of 5x space savings. So a 20 terabyte array should be able to handle up to 100 terabytes in that world. So why this matters is because if dedupe is post-process and you ingest a large amount of workload throughout a day and it's not going to dedupe that later, well, think about storage vMotion. Let's just say you vMotion a new application onto the array that is only 5 terabytes. Well, it might in the future dedupe and stuff like that to save and move down to 1 terabyte. But if you were down to 5 terabytes of physical storage left, what impact is that going to do to not only either crash your array, but also if you're taking up the majority of the usable capacity left, what's that going to do for write amplification for all the other applications on the array, right? So understanding that post-process isn't necessarily going to be effective, but on top of that, understand if it's inline all the time. So there's a few vendors out there that will say they do inline, but the reality is they might do inline for 20 to 40% of all writes to the array. And why is that? Because they don't have enough CPU power to continue to handle deduping everything. They save CPU cycles by deduping what they can. The rest of it they'll write fully hydrated, and then they'll do a process on the back end to come back and dedupe that later. Now, is that good enough for a lot of people? It is. But is that something that you want to understand? Because that might impact a certain application you have that might be write heavy? Absolutely. And then also variable block dedupe. Some vendors will dedupe at 1 block size, right? They might dedupe everything at a 32K block size. Well, the reality is, if you have a mixed workload environment, they're probably not going to both be the block size. 2 applications aren't going to be both block size. So being able to set each application at its own block size for dedupe is going to not only give you better space savings, but it's also going to maintain integrity within the application, right? Cutting up those blocks within an application isn't necessarily going to be ideal. While it's rare that you're going to have some sort of data corruption, you're putting yourself in, you're exponentially increasing those probabilities. Even though if it goes from 1 in 100 million to 1 in 1 million, that's still probabilities I don't typically like. And then, like I said, understanding that dedupe tax, right? Understanding what the performance levels can be with it turned off to allow you to make that intelligent decision, right? Making that decision informed is always the direction you want to go. New bottlenecks. So I touched on this a little bit earlier, right? New bottlenecks have come up as to the forefront since the introduction of AFAs. AFAs offer all of the IOPS in the world, right? I can do 200,000 IOPS, I can do 1 million, scaled out to this, I can do 2 million IOPS. Well, that's great.
But now what else is going to stop those IOPS from mattering by increasing the latency within my environment, right? So disk IOPS are no longer being the bottleneck. What should you look out for? Some of the key things to look out for are throughput. So SSDs, while also well known for having nearly 10x the throughput of spinning disk, well, with dedupe and compression, often that same amount of data that typically would be read or written to, let's just say, 100 drives, now all of a sudden it's being read or written to a mere 10 drives, right? Maybe 15 drives, 20 drives. So yes, it can offer up to 10 times the throughput, but you might be reading or writing through 10 times less disk. So understanding throughput has become, excuse me, much more important to understand as you're evaluating the AFA landscape. CPU exhaustion. So one thing I see out there is more upgrades are happening within the all-flash world because of CPU needs than there is of IOP increase. So typically, you might have enough SSD to handle all the IOPS that are available. It's typically CPUs that can't handle that. Typically, you're doing some sort of controller upgrade to improve performance than you are needed to do a disk upgrade or expansion, right? So keeping an eye on CPU and making sure that the vendors you're looking at, that the controllers can handle the IOPS. We don't live in the same world that we might have in the past where, hey, I've got 24 SSD drives in this configuration. I'm calculating them all out at this 8,000 IOP range. I should be good. Well, if the controller can't handle that 100,000 IOPS or that 200,000 IOPS, then it's not going to matter how much IOP capability you have in the disk if that's your bottleneck. So I'm seeing a lot more CPU as a bottleneck than ever before, as well as throughput as a bottleneck than ever before. So now let's talk a little bit about how you test an AFA. So a lot of the tests I've seen in the past are very similar to what I'll call the hero test, right? IDC refers to it as a hero test. Doing extreme amounts to see what the max capability of an array can be. I'm all for testing out the limits, and that's great. But a hero test doesn't necessarily give you much valuable information, right? I see customers say, I tested 100% write and 100% read. Well, and then I ask, what application do you have that does either one of those? And the answer is none most of the time, right? There are those rare instances that's 95%, but if that's not reality, if that's not real for your environment, why test it, right? What's the point? What value is that giving you? What's that information for you if that's never your environment? So it's really best to understand what your read-write ratios are, test at that level, but also test at your block level, right? Make sure you use a tool that can give you block options so you can get that as close to real time as possible if you can't test actual workloads, right? Also test the AFA with capacity. So again, this is why I gave that sort of introduction to SSD hardware and what its limits are, is so you can understand testing the AFA at a used capacity. And I'm not saying you have to fill it up, right? I don't think any array performs well at 100% capacity, but where's that drop off? When I test it at 50%, where's performance at? When I test it at 70%, where's the performance at? When I test at 85%, 90%, where's the performance at? I don't like being told that once I hit 65 or 70% of my purchase capacity, I need to upgrade or performance is going to fall through the basement. That's not something my customers like to hear, and that's not something that I like to hear for something I've positioned for my customers, right? So understanding where that sort of what I'll call that cliff drop-off in performance is going to be is something very important to know. All right, when should I start evaluating capacity upgrades or performance upgrades within my AFA? Also, can it deliver that consistent sub-millisecond average? So a lot of AFAs, either whether it's capacity limits or when you hit a certain amount of IOPS, it'll keep going, but you'll start seeing those latency spikes back to that traditional spinning disk level performance, right? You'll start seeing 5 milliseconds, 8 milliseconds, 10 milliseconds. So making sure that at your workload design, speed, whether it's 60% read and 40% write with 8K blocks, with a 60% capacity full, making sure if that's what you desire, making sure at that level of testing, it'll maintain the milliseconds and the performance numbers that you want to see. So the IDC has released, a good amount of testing framework. So Class A testing is typically referred to as that production workload. So what I like to recommend for my customers, if possible, this is also going to be probably the most infrastructure intensive and also the most timely. But if you can, put an actual production simulated workload environment, right? So whether it's restoring from a backup in a siloed environment for those tests, for at least a portion of it, right? Whether it's a fragment of actual production size or not, that's going to give you the most realistic information. A Class B is using generated workloads from an app-specific tool, right? This can also be very accurate. This is one that I see very consistently. Also very time-consuming, and something that is a little bit more time-consuming now that people are doing a lot more of multiple workloads. When AFAs were a point solution, it was a lot easier to say, hey, I'm putting my SQL environment, so I'm going to just do a SQL test. But now that people are saying, hey, I want to put VDI, SQL, and Oracle, and Exchange all on this environment, right? It's a lot more time-consuming to do app-specific work testing because now you're having to do it across 4 or 5 different apps. Class C testing is a little more generic, generally a more time-efficient than A or B. This is where you do very specific tools that just simulate certain block sizes, things like that. Might require some sort of scripting skills. Apps like VD Workbench or VD Bench, is a good example. Stuff that's out there. Class D, also this is going to be typically use a lot more scripting, but a lot less of an infrastructure need. Also pretty common, but I typically see C used a lot more often. E is that old school test. Let's just try and hit every limit of the array and sort of go from there. I see, at least with my customers, it's not being used as much anymore. That's typically the type of guidance I try and give, is stick with something along the lines of C, and let's see where we can, or at least let's find a balance in here, of where we want to go. Here's a sample test plan. So everyone knows about test plans, but the reality is most people don't use them. They'll get the toy, right? They'll put it in their environment, and they'll just hit it hard. But one thing, I always recommend doing is actually documenting what you're doing, test out various levels, and then also document whether or not you succeeded, right? What were the metrics you were seeing? I know I shouldn't have to say this, but the reality is I'd say less than 25% of my customers that test start off with a test plan. Oftentimes I create that for them, and then it's really a crapshoot whether or not they actually follow it or not, because time constraints are always there. So I want to recap some key points. All right, understand your desired outcome. All right, what's the AFA improving? What is increased performance going to do for the business and IT's ability to support the business? Understand the features, how they apply to your environment. Those features, right, with the same name across different products, understand how they're going to work, right? Just because every product offers dedupe and compression doesn't mean it's going to work the same way across all the products. And test to get as close to real world as possible, right? Everyone has a job to do, and that's always going to be a time constraint on your availability to test. Find that balance. Do your best to be able to test real world. That's the only way whether you can, to really find out whether or not it's going to solve the challenges you have within your environment. I hope this was some good information. I know we've got about 13 minutes left, but I wanted to leave some time for some questions and answers. Hopefully, maybe as we've gone, you've typed out some questions to Rachel in chat. But now is the time to ask. So what questions do I have out there?
Okay, so we'll start with the chat questions. We had a couple come through. What are some of the best AFA products out there?
So it's a good question. I would definitely start off by saying that it depends on your workload for the most part. Some AFAs are very much designed for very specific workloads. I would say some of the most popular products out there, some of the best performing actually, I don't want to say most popular because it doesn't always mean good, are probably Nimble's new AFA is one of the better ones. From a ease of use standpoint, combination of ease of use, performance, the fact that it integrates with their hybrids of a big differentiator. Pure Storage is definitely one of the leaders in the AFA space. They have a good refined product that does things at a very cost-effective level compared to some of the other products out there like Extreme IO. So Extreme IO from EMC is also a good product, very costly, right? Very expensive. And all those products have some of their challenges. Definitely something to discuss at a different level. But those are three of probably the most popular products out there. Another one's HP 3PAR. I see that mostly being used in all HP environments just because, HP gives a discount, that type of thing. But I do hear that name out there in the AFA world a little bit, more than some of the other, small scale ones out there.
Okay. Is there a certain type of SSD that is better than the others?
I would say 3D NAND. I know I touched on that a little earlier. NAND technology is changing. While SLC might have the best overall peak durability and performance numbers, it doesn't scale. And if SSD, it doesn't scale quite the way 3D NAND does. Well, not even close, actually. It's still stuck under a terabyte in size. And the performance and durability numbers aren't different enough. We're talking a couple % difference. There's been extreme advances in SSD to help maintain performance across the different SSD types. So while there was sometimes back in the day between SLC and maybe MLC, there was a 30–40% performance difference and a 50–60% durability difference from SLC. That's no longer there. We're talking a couple % difference between maybe 3D NAND, if any at all. There's actually been a number of independent testers that have said there's pretty much no durability difference and not much of a performance difference between them. So I would say 3D NAND, from a sheer capacity standpoint, because it helps drive down that price per gig, which is probably the #1 limiting factor from people being able to move to all flash arrays for almost every workload.